Um, so this was the theorem that we were after. So if we have an injective immersion to some large dimensional Euclidean space, this we know that there exists some such immersion, right? So well, we know that for compact manifolds, but anyway, the theorem is about any manifold. As long as you have an injective immersion into Rn, n is large enough, then there also exists an injective immersion to one less. Okay, and you can apply this theorem repeatedly until you get to 2k plus 1. And so for a compact manifold, of course, if you have an injective immersion, it's the same as an embedding. So this proves Whitney's theorem in the case of a compact manifold, right? And so we were almost done with the proof of this theorem. So what was the idea? Well, the idea was if you have some immersion phi from M to Rn, then you post-compose it with a projection to some hyperplane. Okay, so this hyperplane was like P of some V. It's determined by a choice of a direction in Rn. So that's a point in this real projective space. And so this is the projection. And the point is that you can choose a direction and a hyperplane so that this post-composition of the projection is still an injective immersion. And once you have that, then you've got a new injective immersion to something which is one less, because this hyperplane is Rn minus 1. Okay, so this was the idea. Okay, and so far we were able to show that there exists a V so that this composition is injective. Okay, because if it is not injective, then it amounts to showing that this V belongs so belongs to the image of this map, and then by Sard's theorem, or by the corollary of the mini-Sard theorem, we know that the image of this map has measure 0. So we can always pick some vector v, or direction rather, direction v, which is outside the image of this map, and so for that guy, this composition is going to be injective. Okay, so we've gotten one of these properties. Now we also need some to make sure that this composition is also an immersion, right? So how does that work? Well, first of all, notice that we didn't just find one V. Most V's in this space work because the image of this map has measure 0, right, by Sard's theorem. So there's a full measure set of possible V's that we could have chosen, and we'll use that that freedom that we have. So what's this? So this is our next time now. So this is, let me just sort of continue here and finish off the proof. So the second thing is sort of to ensure that it's an immersion. So if not, so if this composition is not an immersion, what does that mean? Well, it means that there exists some P in M and some non-zero tangent vector in the tangent space at M, so that the derivative dp of this composition, let me just write it more clearly. This is this composition that is not an immersion, and it means that there is somewhere this map is not injective, so this derivative is not injective. So there is some such P and a non-zero tangent vector that maps to the 0 tangent vector in the image, right? The image is some tangent space to a point in Rn minus 1, right? So that's how we are thinking of this hyperplane. right? So, and now this, by just the chain rule, if you like, it's this is the basic properties. So this is the composition of, it's a derivative of this composition, so it's the composition of the corresponding derivative. So it's this composed with d. Well, I shouldn't say. Yes, it's dp of phi here, and then it's d. It's a derivative of this map at phi of p. Okay, so let me not write that. Okay, so it's a composition of these two derivatives by the chain rule applied to x equals 0. Now, but what is this? This is equal to pi of v because this is just a linear map. So right, so it's a projection of the whole space Rn to so recall. So what is this? Recall that pi of v is this projection from Rn to this hyperplane, which is Rn minus 1. So it's a projection along this, sort of direction v, whatever this direction is, plus or minus. It's a so you're kind of projecting to this hyperplane, right? So
Sir, your voice is breaking.
Oh, can you hear me now?
Yes, sir, can you repeat it? I mean, after.
Okay, so I was just reminding everyone what this pi of v is. So the pi of v is this projection map from Rn to this hyperplane, right, in the direction v, and it's a linear map. So the derivative at whatever point it is, I didn't write down the point over here. The derivative is going to be the same as the linear map. The derivative of the linear map is the same. So if you do have some vector which this linear map sends to the 0 vector, then it's the same as saying that pi v of this, whatever this vector is 0. And pi v is 0 if, if and only if sort of this dp phi of x is in the same direction as v. Okay, so that's the direction that gets collapsed in this linear map. So the derivative of this this linear map here is the same as its derivative, but this linear map here, it is 0 on vectors that go along this direction v. Anything else, it's sort of it goes to some non-zero vector, but these guys they get collapsed, right? So if this composition is zeros, and whatever this vector was has to be in this direction v. Okay, so in other words, if something is not an immersion, then if we look at okay, so then we'll be able to say something similar to what we had last time. So we can say that V is in the image of a smooth map, which I can define as follows. It's a smooth map beta going from the tangent bundle of M. So this is where the tangent bundle comes in, minus this is the 0 section. I'll describe what it is, to Rpn minus 1, which goes by taking Px goes to dp phi of x. Okay, so so for every point on the manifold and every tangent vector, you can look at dp phi of x, right? And this is going to be well defined unless x is equal to 0, right? And x is equal to 0, dp phi of x is 0, right? And that doesn't define any, it's a 0 vector in Rn. And so that doesn't define any point in Rpn minus 1, right? So to make it non-zero, you have to throw out the 0 section. So this is what I mean by this minus of 0. So this is basically, this actually represents the 0 section, and we'll talk about sections later on, but right now what it just means is all the zero vectors on these tangent spaces. Okay, so it's 0 in TPM. So so if you collect all, so you can throwing out this subset of the tangent bundle, right? And so you're left with all, all the non-zero vectors in every tangent space. And so from there you have this map. Now it's well defined, right? And this, what we just discussed, if your V lies in the image of this map, right? So then it's not an immersion, right? So then this composition pi V composed with phi is not an immersion. But if it is not in the image, then, I mean, all these implications, as I said, are reversible. If it's not in the image, then we are okay. We are good. All right. So so now, what are the dimensions? Again, we can now apply Sard's theorem. We know that the total this tangent bundle, this Tm, is a manifold. It's a 2n dimensional manifold, and you're throwing out this zero section. This is like a closed subset of that. So it's going to be, so the this whole thing is a open submanifold. It's an open set, is sitting as a submanifold of this of Tm. Okay, so let me just write that. So the domain of beta is a 2n dimensional manifold, and target is, as before, is a n minus 1 dimensional manifold. And from our assumption that we had, 2n is strictly less than n minus 1. Okay, and so we, by the Sard's theorem, or the corollary, the mini Sard theorem, let me just say Sard's theorem, we have the image of beta has measure 0. And if the image has measure 0, then certainly we can pick some v which is not in the image. Okay, and for that v, this composition has to be an immersion, right? And so so we are kind of using Sard's theorem here. And how do you ensure both 1 and 2? So you have to pick a v which is, so that it's not in the image of this map, nor is it in the image of this map. Well, that's easy, because Sard's theorem tells you that, all such good v's for us have full measures. So the intersection of two full measure sets is also full measure. So we are okay. Okay. So so the pick v so that it is neither in image of alpha, which we discussed last time, or nor in the image beta. And this is possible because, you're just trying to avoid a measure 0 set, right? And so this V works, proving the claim. Okay, so the claim was, I mean, so that there is some V. Remember, this was the key claim. There exists a V for which this composition is an injective immersion. And basically, it wasn't just the key claim, it was the basis of the rest of the argument. It was the main part of this. So the proof is over. Once you prove this, you're done, right? Okay, so any questions about this? Let me just update the notes. So while this happens, you can let me know if there's any question. All right. So so if this is okay, so now we've sort of proved Whitney embedding in the compact case. So now let's go on to sort of Whitney embedding. Just let me just say this sort of So now let's work with, so what happens, what are the arguments when the manifold is non-compact? Okay, so the first thing we need to do is we need to be able to immerse into some Euclidean space. Let me start with that. Okay, so so the theorem that we'll start with is so any non-compact smooth manifold. Let me just write it. I mean, it's clear. We are all the time working with smooth manifolds. So maybe it's redundant writing that, but so, and it's k-dimensional. Let's assume it's k-dimensional. So any non-compact smooth k-dimensional manifold admits an injective immersion into Rn for some n. Okay, so let's start with this. Okay, and then we'll try to get it down to 2k plus 1, right? And in fact prove that there is an embedding, right? That's what we are after. Okay, so yeah, once we prove this, we can get it down to 2k plus 1 because of the previous, what we just proved, right? What we just proved doesn't care about whether the manifold is compact or not. So you can just apply the same argument to, reduce this, this dimension of the target by 1 each time. As long as is it bigger than 2k plus 1, you can do that. So you have to stop at 2k plus 1. So once you have this theorem, a corollary would be that, sort of that any manifold, any such manifold has an injective immersion into R to the 2k plus 1, the previous theorem. Okay, so so maybe I should write that. So corollary by the previous theorem we just finished proving is that any such Mk has an injective immersion into R to the plus 1. All right, so we have to start from somewhere. We have to first show there is something in Rn. And our previous argument for compact manifolds doesn't work because we don't know whether you have finitely many charts covering M of Mk, right? So you can't quite do that earlier argument we did. So what do you do? Well, we can do the following. All right, so so let's start with a smooth exhaustion function. So that M to R, M is an uncompact manifold, be a smooth exhaustion function. So remember what this was. This was a function which was a proper function, right? So a smooth function so that these sub-level sets were compact, right? So so this we had constructed earlier, if you remember, using a partition of unity, one of the first applications of having a partition of unity. And so so once you have this smooth exhaustion function, we can use that and its pre-images to sort of reduce to the compact case in some sense. So let's try to understand that. So you define Mi, let's call the index with I to be the pre-image of this interval I comma I plus 1. So it's a closed interval on both sides. So it's like this. So your function I plus 1, I plus 2, etc. So each of these intervals that only kind of meet in at the integers, right? So each of these pre-images would give you compact sets, right? Because this smooth exhaustion function by definition is a function. So the pre-image of a compact set is compact. So these are compact subsets of M. And since these are compact, so let me just say that since these MIs are compact, So we say is because I've, let's say, chosen some arbitrary mi. So since each mi, maybe I should have said each mi is compact, it can be covered by finitely many coordinate charts. Let's call them U1 to UK. Let's pick one mi. Okay, so this is, although this is for each I, each integer, we kind of so this is for each I in n, but let's focus on one such mi for now. And so because I don't want to keep adding too many indices here, so this maybe the number of coordinate charts would, this k would depend on I, but I'm not going to write that down. Okay, so right, so you have this this compact subset. You cover it with finitely many coordinate charts. Now the only thing is that it's not, we don't quite know whether it's a manifold, right? But we can just thicken it a bit. So we can choose some slightly larger open set containing these mi. So we can first of all, we take the union of these finitely many coordinate charts, okay, and this might be too big. You might be, kind of maybe these themselves would work, but I'm going to sort of intersect this with f inverse of an open set, which is something like I minus some epsilon and I plus 1 plus epsilon. So something slightly larger, so sort of something slightly larger. And so now in the pre-image, it's going to be some open set containing mi, right? And so and ni is an open set. Okay, so it's a you're taking well, this is an open set clearly, and this is an open set. This whole thing is a open set in a bigger manifold, so it's a submanifold, right? So this ni is now an open submanifold of n, and containing mi. Okay. Well, maybe that doesn't really. Well, we might not need that actually, but what's important is that by construction, now if you vary your i's by construction, these n sort of each of these ni's can be covered by finitely many coordinate charts. Okay, and what happens is, and this is number one, and number two is, so there are two things that happens with construction, and the other thing is that is ni, this ni intersection nj. These is phi if these indices are bigger than equal to 2. This is just because when we are taking these open sets, this is where this intersection with this slightly larger open set comes into play, where if you take this guy and you take for the next guy might intersect. So the preimage of this interval, let's call it I plus, well, it's slightly larger than I plus. Anyway, so the pre-image of this green guy, this corresponds to ni, right? And this pre-image of this is ni plus 1. So these might intersect because there's a little bit of an overlap here. But if you look at the next guy, so ni plus 2, that has no chance of intersecting with ni, right? So this is, again, this is one feature of this construction, right? And we're going to use this fact that we've nicely constructed. Okay, so now we've gotten this, so we've, from this bigger manifold, non-compact manifold, got this kind of inside it, we've kind of have this collection of these open sets, these submanifolds. Now each of these can be finitely, covered by finitely many coordinate charts, and each of these sort of are kind of, they don't overlap too much. They're sort of somehow they're locally finite, if you like. And so we can use our previous arguments now. Okay, so the first thing that we can note is that so the sort of this first property, let me just say this implies that there exists an injective immersion. So let me call it, instead of one, let me call it injective immersion of ni to into r to the 2k plus 1. This we know from our previous arguments, right? Because we know that if it's covered by finitely many coordinate charts, you have an injective immersion into some large Rn, and then we just saw that you can just reduce the dimension one by one until you get to 2k plus 1. Okay, and so each of these can be injectively immersed into 2k plus 1. So now we're going to use that. Okay, so actually let's call that, let's give it a name. So this let's call it phi from ni to r to the 2k plus 1. Okay, so we're going to now use these guys to put together some injective immersion of the bigger manifold. So now let's start with some kind of bump functions. So this be a smooth function such that this rho I is 1 on mi, but it's 0 outside ni. Okay, and the support of rho I is contained ni. So remember that, okay, maybe I shall add that by construction. You have this third thing, which is that sort of ni contains mi. So mi were these compact sets, the pre-images of these closed compact intervals, I plus 1. And so by construction, so these ni's contain this mi. And so we can certainly choose from, this is something like this, so like what we've done before, right? So we can choose some, yeah, so we have a sort of compact set, we have a slightly larger open set containing it, so we can choose some smooth function which is 1 on mi and 0 outside it, right? So sort of outside it, it's 0 and 1 there. So this you can easily do. You can use partition of unity if you like. I mean, this is like, maybe it's like one of the exercises you had last week, right? And then you define, so once you have these collection of these smooth functions, bump functions, you can define our injective immersion of m into r to the 4k plus 3. Okay, so we can, so right now we haven't gotten yet to 2k plus 1, but we just wanted some n, capital N, if you remember. So, but our capital N would be 4k plus 3. So, and we can define it as follows. You can take a point P and you map it to the summation of rho I of P, phi I of P. This is sort of, this is when I is odd. Okay. And and the summation. So these are now like I'm adding vectors in R to the 2k plus 1, right? So so there's a phi I of p. So this phi of p where I is even, and why even and odd should become clear in a minute, and comma f of p. Okay, so these guys, so this lies in R to the 2k plus 1, this lies in R to the 2k plus 1, this is in this is, remember what was f. So f was some function, right? So it's a smooth exhaustion function. So this is just a point in R. And so this whole vector now lies in 4k plus 3, 2k plus 1 plus 2k plus 1 plus 1. Okay, so so if you define it like this, then so the first thing to notice is that yeah, so this is certainly well defined, right? And so and if you divide it like this, so so what happens is, it's what happens is, so both the terms cannot be 0, I think. So the point is, or both the terms cannot, well, okay, so this point P has to belong to one of these MIs, right, by definition, right? So now it can only, right, so now let's see, what's the point? Right, so right, so this point P must belong to one of these MIs. So for that, so that I, so the row I of P will be non-zero. Okay, and phi I of P will be non-zero because phi I, remember, is an injective immersion into this. So anyway, so okay, so maybe we'll need that in a little bit. So, but the claim is that this is the map that works. Okay, so this, let me just write that down first. Right now, this is okay. This is well defined. So the claim is that phi is an injective immersion. Okay, this is really the map we were looking for. So the proof is that, first of all, it's injective. And why is it injective? Well, so if you have phi of P1 equals phi of P2, then what happens is that there exists some, so if you, so then what happens is this f of P1 will be f of P2, right? So so let me just say then f that, because that's that last coordinate there, f of P1 equals f of P2. Now this lies in some closed interval I plus 1. Okay, so that exists, so we get an I here, right? And so so this so P1 and P2 are contained in MI, are both contained in MI, which is contained in capital Ni, right? This is right because MI was the pre-image of this I plus 1, right? For some I, right? So this is belongs to this. Let me just write it for some I, right? So for some I, it belongs here. And by definition, P1 and P2 belong to mi. This part is just sort of following the nose basically and sort of proving what we want. And so this means, what does this mean? It means that in this sum that we had, right? So phi 1 of p. Oh, so the screen has stopped. Okay.
Yeah.
Yes, sir.
All right. So I don't know why that has happened. So let me. Can you see it now?
Yes, yes.
Yes.
Okay, fine.
Yeah.
All
Sir,
right.
can you update the notes once?
Okay, sure. Yeah, this is lecture 10. Okay, so you have to click on the. All right. So right. So what happens to this now? The sort of even and odd business would become clear. So what happens is so notice that so if you sort of just have these odd indices here, so they differ by 2, right? And if they differ by 2, we kind of notice this fact that these ni and nj's, they don't intersect if they differ by 2, right? So if it is non-zero somewhere, then all the other terms would be 0, right? So so basically so what what this amounts to is as sort of is that this phi I of p1 would equal to phi I of p2. All right, because if you look at those corresponding terms in the two vectors phi of p1 and phi of p2, then the only surviving thing would be well, you'll have a rho I of p1 also, but that is 1, right? So rho I of p2, but these are 1, so these won't sort of, you can cancel these out, and what you're left with is this. All right, but you know that phi I is injective, right? It's an injective immersion, so which means that p1 is equal to p2, and this is what we were after. Right? So this is the argument for injectivity, and immersion is actually sort of simpler. So because suppose you have some point p in well, p in m, let's say, and suppose you have so what is the derivative of phi of p, and you apply it to x. X is something in is sort of is, let's say, maybe I should write it somewhere else. Sort of x is something non-zero and belonging to the tangent space at m. Now, so this would look something like, if you think about it, it'll look like dp of phi I at x, comma, something, which we don't care. If I is, so if p belongs to mi where I is odd, or it looks like something dp of phi of x star if I is even. Okay, so that is p will belong to some mi for some I, right? And so so in either case, as I said, in the sum of odd or even, the only term that really survives is phi I of p, right? And so the derivative of capital phi over here it'll just involve the derivative of phi I of p, and that guy is non-zero, okay, because phi I is an immersion. So this is non-zero here, this is non-zero here. Oops. And so hence, so for any of these p's, this dp of phi x is non-zero. Okay, so it can't all be 0, and so that proves that it's an immersion. Okay, so I hope that was clear. So we kind of we do get some injective immersion into a Euclidean space. We don't quite have an embedding yet, right? So right now it's still just an injective immersion, but we have something into some Euclidean space. All right, and once you have something into some Euclidean space, here it was 4k plus 3. As we notice, we can get this 4k plus 3 down to 2k plus 1. Okay, so so if this is fine, let me just update the notes. Let's now sort of prove what we were after. So now we can just prove the statement about embedding. So any smooth K-manifold embeds in R to the 2. All right, so how does that work now? Well, so you have an injective immersion to 2k plus 1 from all that we discussed. Okay, so this is something now that we have now. Okay, and we can also ensure that this image is a bounded set in R to the 2k plus 1. It's contained inside the ball of radius. And why can you ensure that? Well, it's just because, I mean, R to the 2k plus 1 is actually diffeomorphic to a ball of radius 1. Okay, so maybe I'll just write it like 0 and 1 inside R to the 2k plus 1. There's a diffeomorphism. This is something that you probably all know, right? And so you might as well, imagine that, if your initial thing wasn't lying inside a big ball, you just sort of post-compose by that diffeomorphism and sort of push everything inside a ball. So we can always assume that this injective immersion has this kind of bounded image. Okay, all right, so this is what we start off with. Okay, and we also need this exhaustion function. So I guess I already used f here, unfortunately. So let me call this exhaustion function rho now. So m to r be, so again, so let me remind you that an exhaustion function is proper, right? The pre-image of compact sets is compact. That's the sort of the thing about an exhaustion function. Okay, so the defining feature of an exhaustion function. So rho is a proper exhaustion function, and now we define a new immersion, capital F, from M to R to the 2k plus 2, that takes f of p, let's say, let me call it f of x. Let me use x as points in M, equals little f of x comma rho of x. Okay, so we're kind of, we're trying to get to an embedding, and so right now it's, it's just an injective immersion. And we want to get to something which is also proper, okay, and that's when we know that we have an embedding, right? And so the first step is to sort of increase the dimension by 1 by adding this proper exhaustion function as the last coordinate. Okay, so by proper, so if you want something which is proper, the map to be proper, you want to sort of have the property that if you go out in the manifold, to infinity, you must be going out in the image. Okay, so if you add a proper function as your last coordinate, this map is proper. Okay, so it's going to be, sort of, it's going to diverge to infinite. The image is going to diverge to infinity whenever x diverges to infinity in M. So this is sort of one trick to get properness, but except that we have kind of increased the dimension now, right? It's 2k plus 2. We want to get to 2k plus 1. Well, we'll project back to some hyperplane. So this is what we want to do. So so recall that we can pick some v in R p to the 2k plus 1, I suppose. It's a direction in R to the 2k plus 2, such that the projection pi from this guy from M to this hyperplane, this is what we kind of started off with. This is the hyperplane. Let me just write that down properly. So it's a hyperplane orthogonal to V. So this, I mean, this is also R to the 2k plus 1, is still an injective immersion. So we know that we can do that, right? And moreover, we know from that argument, we can pick, there are lots of choices of V. So we can pick V not equal to the vector or the direction given by 0, 0, 0, 0, 1. Okay, so we know that we have that choice, right? So we have a full measure set of points we can pick. So if we don't want this particular point, we can do so. Okay, so we pick something which is not this, and we'll see why this is going to be important. Okay, so the claim now is that pi v for this v not equal to that, and still in injective immersion, this guy is actually also proper. And then we are done, right? So then we would have, some such v, which is the composition is an injective immersion and is also proper. So that's an embedding. Okay, so so we can pick something, and so what's the proof of this? This is where we will use the fact that v is not 0, 0, 0, 1. Okay, so what do you mean by showing that it is proper? So we want to prove, so we need to prove that the pre-image of compact sets is compact. So we need to prove the following, that for well, it's let's say, I mean, so let me just say it's enough to prove the following. So it's enough to say that for any c greater than 0, there exists a d greater than 0, such that if you look at all the points in M, so that I'll just call it, so this is less than equal to c. Actually, I'll drop this subscript here. It's sort of, it's cluttering my notation. I'll just call this projection is, I'll just call it pi. Okay, so this set, so this is actually the norm in Euclidean space, right? So so this Euclidean space is R to the 2k plus 1. All right, so you're looking at so this this set, I want to say, is contained. So this is like the pre-image of a compact set. Okay, so if you think about it, this is the pre-image of the ball, closed ball of radius little c in R to the 2k plus 1. All right, so I want this to be compact. This is such the pre-image to be compact. So so it's enough to prove that this is contained in all the points in M, so that the size of rho of x is less than equal to d. This guy is compact because so let me just say, so this guy, this is compact since rho, this exhaustion function, is proper, right? And this is the pre-image pi composed f, the pre-image of a ball of radius c, closed ball of radius c inside R to the 2k plus 1. So if I can prove the sort of the pre-images of compact sets in R 2k plus 1 is compact, then we are done. It's enough to prove that pre-image of these closed balls, these closed and compact balls in 2k plus 1 is compact. And for that, it's enough to prove that if you have such a pre-image, it's contained in this guy, which we already know is compact. Okay, so it's enough to prove this, and then we'll get proper, and then we'll be done. Okay, so how do you prove this? Well, suppose not. Suppose it's not true. Okay, so if not, so what happens? So then we get, so if you look at the sort of the contrapositive of the sort of negation of this, statement, you'll find that there should exist a sequence of points xi in M such that this guy is the norm of this is less than equal to less than or equal to C, but rho of xi, the size of that goes to infinity. Okay, that's the negation of this property not being true. Okay, so there exists a sequence of points so that this guy is satisfied, but it's not contained in anything. You can't find a D, so that so this rho i's need to go to infinity. All right. Okay, that's fine. So, so how does this give a contradiction? So by definition of projection, remember there's a projection pi is along the direction of v. So this f of x, a capital F of xi minus pi composed with f of xi, this is multiple. It's a vector in R to the 2k plus 2. Oops, let me just write it more neatly. So this guy is a multiple of this vector of v. So not the v in R to the 2k plus 2. And let's give this a name. Actually, let's sort of divide this by rho I xi. So this guy is also a multiple of v. I've just scaled it, and I'll call this wi. Okay, so so what we are going to do, so what you notice is that, so remember this f of xi was f of xi comma rho of xi. Okay, if you divide by rho I, so this is sort of note, so divide by rho of xi, you get f of xi by rho of xi comma 1. Okay, and what happens when I tends to infinity? Well, remember that at the very beginning we chose this f to be bounded, right? It's if you go back to the sort of the first line of our argument, this f satisfied this boundedness property. It's all contained inside a ball. And so if you have this setup where these denominator, these rho of xi's are going to infinity, then so this guys will all go to 0. And so this f of xi divided by rho of xi, this goes to the vector 0, 0, 0, and the last one is just 1. Okay, all right. So and moreover, so if you think about what so that's where these guys go. Okay, so remember I'm sort of we're basically interested in where these wi's go. Okay, so the first term is f of xi divided by rho of xi. So that goes to 0, 0, 1. What about the second term? Well, the second term, so pi composed with f of xi, remember that is bounded. We are kind of assuming that this is true, right? So this guy divided by rho of xi, the norm of this would be less than equal to c upon rho of xi. So that goes to 0. Okay, so this goes to 0 as I goes to infinity. So so this second term actually just gives you the 0 vector. Okay, so this goes to the 0 vector as I goes to infinity. Okay, so if you put these two things together, we see that these, when you look at this difference, these wi's go to 0, 0, 0, 1. Okay, so so the conclusion is that these wi's go to 0, 0, 0, 0, 1. But these wi's are always multiples of v. Okay, so if a sequence of vectors which are all multiples of v go to this vector, then v must be a multiple of this vector, which is a contradiction. Okay, so since each wi is a multiple of v, so is 0, 0, 0, 1, which is a contradiction. And we are done. Okay, so so we are kind of also done exactly almost at 4. But anyway, so any questions about this argument? So we had picked v not to be 0, 0, 0, 1, right? So but if we assume that this composition is not proper, then that contradicts that choice. Okay. All right. So the sort of this concludes the proof of Whitney embedding theorem. So now we know that these manifolds that we had defined abstractly as this basically piecing together charts and sort of it's just a topological space with this property of being locally Euclidean and having the smooth atlas. So you can actually also think of it as a subset of some Euclidean space. It's a nice subset of Euclidean space as a submanifold. Okay, so and sometimes I mean that's another sort of way that one starts thinking about manifolds as these nice subsets. Okay, so in some books you would see the definitions of a manifold as submanifolds of Rn, and then you kind of do various things with it. But this now we know that the two are basically the same, right? So we have this Whitney embedding theorem, and as I said, you can do better. You can get to 2k, not 2k plus 1, but that's the optimal. I mean, yeah. So I mean, for example, even for a surface, we know that we can embed it to R4, but not always in R3. Okay, so let's stop here. If you have any questions, let me